Hi all. In the previous video on Bayesian parameter estimation, we learned how to use Bayes' theorem in a rigorous manner to make future predictions based on the training data that we have. But as it turns out, that method is very complicated to apply. Even for the simple case of a coin toss, we had to do several complicated integrals. And then we learned in the videos on maximum likelihood estimation and maximum a posteriori estimation that in practice in machine learning we use simpler methods which are easier to implement. So essentially what we have is a set of data points xi and yi. So this I goes from 1 to up to n and represents the number of data points that we have, where each xi and yi can be vectors in general. So in the case of supervised learning, as you know, the objective of our machine learning algorithm is to find out a function that gives a mapping between the input and the output. So let us denote that function by h, where h stands for hypothesis. So basically what we have is yi is equal to some function h of xi and the parameters theta, where theta is also a vector, plus epsilon I, where epsilon I is the error in the data collection. Any physical measurement of data invariably incorporates some amount of error or noise, and so we have to account for that in our analysis. If there was no error in the data, then actually so much of machine learning would not be required. It would be far simpler to do any kind of prediction. But because we have error, we have to now use various kinds of methods. So here yi is the output, xi is the input, and theta are the parameters that we need to learn. And this epsilon I is our error or noise in the data. Now what we saw in the video on maximum likelihood estimation is that if your epsilon I is Gaussian distributed, then one of the ways of estimating theta is given by this expression. So if epsilon I is Gaussian, then the MLE estimate of theta is given by arg min. Notice that we have a min and not a max, summation over I yi minus h of xi comma theta whole square. So this quantity over here along with the sum is what is called our cost or loss function. And this particular form of the loss function is what is called the least squares error and is what is most commonly used for regression problems. So in that video on maximum likelihood estimation, we also saw that if you have a binary classification problem, then you could use a binary cross entropy cost function. So now how do we find out this argument minimum? So now we have to minimize this function. So again, what we did in those videos on MLE and MAP is that we took a derivative of this function with respect to theta, equate that to 0, and from there find the value for theta. Now that, although is mathematically all right, but it is very difficult to compute analytically, because usually these cost functions are very complicated because these h functions are usually complicated. So in the case of linear regression, which we are going to see in the next video, this h is a linear function, and so in that case, it is possible to write an explicit expression for theta mle, but even then, actually doing the computation is fairly difficult. And so, to handle this problem, there is this famous algorithm called gradient descent, which is actually used in practice. And why is that so? As I just mentioned, that the derivative of the cost function with respect to theta, that dou c by dou theta equal to 0, is hard to solve analytically. Okay, so what do we do? So let's take a simple case, a simple example of C, and then we will discuss the general method. Let's say that your problem, machine learning problem, has a single parameter theta which you want to estimate, and this y-axis is your cost function. And now let's say that the function c of theta is of this kind. So now visually we can say that the minima is somewhere over here. So this is your point theta star at which your c takes the minimum value. Now if you could write an analytical expression for dou c by dou theta, equate that to 0 and analytically solve it, then great. But as I just mentioned, that is usually not possible to do in practical situations. So then what do? We have to use some kind of a numerical method. So now let's take a initial guess. So let's say let's pick up some random value for theta, and let's say that value is somewhere over here. So we have now picked up some value theta 1, let's say at the first iteration. Now we can visually see that our theta star is on the left of theta 1. So now if you have to pick another value for theta with the hope that you will converge to theta star, you should pick up a value which is on the left side of theta 1, because if you pick up something on the right side, you will go farther away from theta 1. Okay. So now instead of doing a visual inspection, can we write a mathematical function that will tell us whether we should now move to the left of theta 1 or the right of theta 1? And the answer is yes, and that is again provided by this derivative of c with respect to theta. So now dou c by dou theta at theta star is 0, but at theta 1 we can see that it is positive. What does that mean? That means that the value for dou c by dou theta at theta 1 points towards the right, but now you need to move towards the left. So what does that mean? That means that you need an algorithm that moves your value of theta in a direction opposite to the direction of the gradient of your cost function, and that is exactly what is gradient descent. So it is descent because you are moving in a direction opposite to the one in which your gradient is increasing. So now you are moving in a direction in which your gradient is decreasing because you need to move towards theta star. So essentially what the gradient descent algorithm says is that you should take a guess for theta and update it such that you move in a direction opposite to that of the gradient. So you update theta so that your new theta is theta minus some eta into dou c by dou theta. And this eta is what is called the learning rate. Alright, so now you take a value for theta. So here we have taken theta 1, and so you take eta to be a small number, and so in the update you move from theta 1 slightly to the left to this new point. Then again you take a derivative, and again you move slightly down, and so on, so forth till you come here. But there will be some oscillation, you will never exactly come to theta star. So when you cross theta star and come here, your gradient will become negative, which means it is in the negative theta direction. So you need to move in the opposite direction. So now what you do is that from here you move in the opposite direction to the gradient, and then you move towards theta star. So you keep doing this iteration till you are sufficiently close to theta star. So you will never ever reach theta star exactly, but that is not important to us. As long as we are close enough to theta star, we are doing fine. So here obviously your value for eta has to be chosen appropriately, because if you choose this learning rate to be very high, then what is going to happen? You are going to jump from theta 1 to, let's say, you may jump over here, and then you may jump further here, and then you may get totally lost. So that is a problem. But if you choose your eta to be very small, then your each step will be very small, and then so it will take a very long time for you to reach theta star. So now that is why choosing this eta carefully is important. If you choose eta to be large, you will get lost, you will never converge. And if you take eta to be very small, your convergence will be extremely slow. And that's why your eta has to be chosen very carefully. Another important consideration over here is that this gradient descent works perfectly well if your function has a shape like this, meaning it has a unique value for the minima. Instead, so now if your function c was, let's say, something like this, then what would happen? Suppose you are at a point over here, then what would happen? Although your minima is actually over here, but from here you will converge to this point, which is a local minima but not the global minima. So these kinds of cost functions are actually problematic, but when you go to complex models of supervised learning, like decision trees or artificial neural networks, there these kinds of cost functions are unavoidable. So in complex machine learning models, you invariably have to figure out a way of dealing with such functions which could have multiple minima. But ideally, we would like to work with cost functions which have a single minima and a shape like this. So these kinds of cost functions which are nice are called convex functions. And ideally, we would like to work with convex functions for our machine learning problems, but unfortunately, that is not always possible in practice. So in the case of linear regression and logistic regression, we will have cost functions which are indeed convex, but as I just said, as we move to decision trees and artificial neural networks, we will find that our cost function is no longer convex. So now one more consideration is here is that how do you compute these dou c by dou theta? Because what is given to you is just the function c. So now you could do it numerically. In science, it is a very routine practice to compute derivatives numerically using forward difference or backward difference methods. But those methods are not very accurate and they cause problems in large machine learning problems. So what we do in machine learning is we use a method known as automatic differentiation. So we are not going to get into the details of automatic differentiation for now, but what is important for you to understand is that automatic differentiation is a very unique method of computing these gradients, and it is somewhere between symbolic differentiation that you do on a pen and paper and numerical differentiation that a typical computer algorithm would do. So it is this automatic differentiation which is the powerhouse of machine learning algorithms, and it is very routinely used for these gradient descent problem. So now one more thing that you must notice is that as we move closer to our theta star, even if you keep this eta constant, your dou c by dou theta decreases, and so your step size keeps on slowly decreasing till you reach theta star. So unless your eta is very high, your convergence in this gradient descent method is going to be fairly good, because dou c by dou theta itself decreases in magnitude as you reach theta star. But there are some algorithms where you may need to use an adaptive method for estimating learning rate. So these are, further complications over gradient descent. So what I showed you is the simplest implementation of gradient descent, but of course there are more complicated implementations which we will briefly see in future videos. So now, as you know that in machine learning there is a problem of overfitting, and why does overfitting happen is because we have this loss function, and if this loss function or this cost function is very elaborate, if it's a very huge model, then it may fit too well to the training data and give you high errors when you actually want to predict the testing data. So for that we use a method called regularization. So again, in the video on maximum a posteriori probability, you saw an example of regularization where we assume the prior distribution of the parameters to be a beta distribution. So in that case, by assuming beta distribution to be the prior, you got a estimate for the coin toss probability which was different from what you predicted from the maximum likelihood estimator. Similarly, in other supervised machine learning problems, there is another regularization method that we use. So your least squares cost function is given by summation of over I yi minus some function h of xi comma theta whole square. So now what we usually do is that if you assume the parameters theta to have a Gaussian distribution, which means that the f of theta, assume theta to be zero mean Gaussian, which means that the f of theta, which is the distribution, will be 1 by root over of 2 pi sigma square e power minus theta square by 2 sigma square. So now if you take a log of this f, and this minus sign will go away because we are now doing a argmin. So what you will get over here is plus theta norm square by 2 sigma square. So here we wrote theta square if theta was just a single parameter, but if it's a vector, then you will have to take the norm. So this is a very simple kind of regularization that we do, and it is often called the ridge regularization. There are other kinds of regularization methods that we are going to see later on, but this is a very common regularization method, and basically what it does is that because we have assumed our parameter theta to have a Gaussian distribution, meaning that we are assuming that our parameter values are small, they are close to zero, because if you remember, a Gaussian distribution looks something like this, which means that our parameter values are closer to zero with a high probability, and as you move away from zero, the probability of theta taking those high values becomes very small. So this cost function now penalizes high values for theta because we are trying to minimize this regularized cost function. So this is one of the ways by which overfitting can be prevented, and to prevent that, now you also need to choose this value for sigma square, because this sigma square is the variance of our distribution and represents the width of the distribution. So if you take sigma to be very high, then the width of this distribution will be very high, in which case your regularization will not work very well and you will undergo a problem of overfitting. But if your sigma is very small, which means that your distribution is very narrow, in that case your theta will almost be close to zero, in which case you will have the other opposite problem of underfitting. So you need to avoid both a very high value for sigma and a very low value for sigma. And so again, the appropriate value for sigma is also something that you have to figure out for your particular problem through trial and error. So this is ridge regularization. There is another method of regularization called the lasso. We'll see these details more when we do linear regression. So now in gradient descent method, this particular gradient descent example that we saw was for a single parameter, but usually in machine learning problems we have multiple parameters. So now let's say you have two parameters in your machine learning problem. So let's say this is your parameter theta 1 and this is your parameter theta 2. And now we don't want to draw a 3D curve, but what we will draw are the contours of the cost function. So what is the meaning of contour of a cost function? So this contour that we draw over here represents the lines on which the cost function is a constant. So these are the lines on which the cost function is a constant. So this is a nice way of drawing a 2D projection of a 3D shape. And let's say this is your value for theta 1 star and theta 2 star, where your cost function takes a minimum. So this line represents a particular value of the cost function. This represents another value of the cost function. This is another value and this is another value. And as you go out, the cost function value increases, which means C4 is larger than C3, is larger than C2, is larger than C1. So now what happens? So let's say you start from an initial guess, let's say which was over here, and then you use gradient descent to move inside this contours till you reach a point which is close to theta star, and then you kind of converge to your desired value. But now instead of these contours being of almost circular shape, although I know it doesn't look like a circle, but they are kind of of similar dimensions. But now instead, let's say that your contours were very skewed. So now let's say your one contour was like this, another contour was like this, Another contour was like this. Now this is a serious problem because let's say you started from a point over here, you may now jump over here, and then you may jump over here, then you may jump over here. And if you take your learning rate to be very small, the convergence will become very small. But if you take even a slightly larger learning rate, then because your contours are very skewed, you keep jumping all over the place without actually converging anywhere. So this is happening because your features have very different scale lengths, and that is why it is extremely important to do what is called feature scaling. So in machine learning, what you do is that you take these features, theta 1, theta 2, theta 3, and whatever number of features that you may have, and you generally scale them to either between -1 to 1 or between 0 to 1, so that they have a similar dimension, and so your gradient descent becomes practically feasible, because if your features have very different scale lengths, then your gradient descent will not work very well. So now to summarize the basic process that we follow in supervised machine learning. So the first thing that you do is choose an appropriate model. So when we say that you choose a model, basically what we are saying is that you choose a particular hypothesis function and the cost function. So this H could be linear regression, logistic regression, ANN, and so on, and your C could be least squares, binary cross entropy, categorical cross entropy, and any other function. Second step is that you divide your data set into training and testing. So the training is for learning your parameter values theta, and testing is to test whether you have learned the parameter values properly or not. And it is important to have a high training as well as a high testing accuracy. Then the third step obviously is to train the model using gradient descent. So when we say gradient descent, it doesn't have to be the simple version that I showed you. Nowadays there are many different ways of doing gradient descent, each of which has its own advantages and disadvantages, which we will see in future videos. But essentially, all these optimization methods in machine learning are based in one way or the other on gradient descent. Then of course you need to have a stopping criteria for your gradient descent. So there are different ways of choosing your stopping criteria. Either you can stop when the change of your parameter values is very small, or you can stop when the gradient of your cost function is very small, or the change in the cost function is very small over every iteration. So what method you use again depends on what problem you are trying to solve, but one of these methods could be used. Fourth point, of course, is to find the training and testing accuracy. So training accuracy again here need not be 100%, and usually it is not. Even though you have learned your parameters theta using the training data, but when you actually apply your learned model to the training data, you will be surprised that the accuracy is not 100% because your training data has errors. And so learning is always inaccurate to various degrees. The more accurate you can make your model, the better you will find the training accuracy to be. But that also depends on the inherent errors in your training data. If your training data is very, very noisy, then no matter what you do, you can never learn the training parameters with a high accuracy. And of course, the last step is that if accuracy is not adequate, repeat the process. So now when I say repeat, it could be repeat from any point. You may have to choose a totally different model altogether. For example, you tried support vector machines and you found that no matter how hard you try, you don't get a good accuracy. You may have to move to logistic regression or random forest or ANN. Or for example, you used ANN and you found the results are not very good. You may have to use some other model. Sometimes logistic regression may also work better than ANN for various reasons. So that comes now under the domain of trial and error. There is no magic wand that you can simply wave and solve your machine learning problem. And that's why becoming a good machine learning engineer actually requires lots and lots of actual practice. You may learn all the theory, you may know all the Python commands, but if you don't have sufficient experience of actually solving machine learning problems, it is unlikely that you will be able to solve a new problem if it is given to you. So now let me end by just again reminding you about overfitting and underfitting. So essentially, in the first step of supervised learning, I mentioned about choosing a particular model. So now on this x-axis, we have what is called model complexity. So at the lower end, let's say you have a very simple model, and here you have a very complex model. And let's say on the y-axis, you have your accuracy. So now for your training data, as you increase the complexity of your model, the training accuracy will generally go on increasing. There may be some very rare instances where the training accuracy decreases with model complexity, but generally your training accuracy will increase with increase of model complexity. But what finally matters is your testing accuracy. And as it turns out that when your model is very, very simple, both your training accuracy and testing accuracy will be low. Then slowly your testing accuracy will improve, but it will reach a point after which it again decreases. So now what that means is that now you have entered into the realm of overfitting. So this is your testing accuracy, and this gap between your training accuracy and testing accuracy is what is called overfitting. And this point where both are low is what is called underfitting. So where you want to be is in this region, which is your sweet spot. Now figuring that out is the major challenge of machine learning, and if you can do this for a wide variety of problem, that is what determines whether you are a good machine learning engineer or not. And that is what you should try to learn when you do machine learning. So now in the next video, we are going to take up a particular form for the model, which is the simplest possible model called linear regression, and we will see how you can use that for solving machine learning problems. Till then, stay connected.